Hello everyone, so welcome to the third lecture of week 4. So we are discussing about RNNs, various applications, and in this lecture we'll talk about how to use RNNs for sequence to sequence tasks. So specifically we will introduce machine translation very briefly as a sequence to sequence task, and then we will see for this seek to seek task how do you use RNN as an encoder decoder architecture. And following on that, we will see how to introduce the attention mechanism to make the translation and other methods models better. So before I start today's topic, so let's try out this problem from the bi-LSTM that we did in the last lecture. So what is the problem? Suppose you're using bi-LSTM for NER, so it's a sequence labeling problem, and there are 3 NER tags: ER, location, organization. And you are using BIO technique scheme. So what does it tell you immediately? So output has 3 into 2 plus 1, 7 dimension, right? Output. Now each word has a 300 dimensional embedding, okay, and the hidden state are 200 and 100 for forward and backward. So what this example tells you is that in the forward and backward RNN, it may happen that you are using a different dimension for hidden states, which is okay because finally you concatenate them, right? So how many parameters are totally to be trained? So for the forward RNN, let's see for the forward RNN, how many parameters? So the hidden dimension size 200 times 1 matrix from hidden to hidden 200, 1 plus from hidden to input 300, 1 from hidden to output, right? 7. In the backward RNN, because hidden dimension is 100, so you have 100 times hidden to hidden is 100, input is 300, and output is 7. So why am I doing that? Because for output you will concatenate. So you will concatenate this and this. So 200 plus 100, 300 dimension will go to output. So the V matrix from hidden to output will be, so 200 from forward, 100 from backward for the same position. So 300 times 7, right? That is the final V matrix, and this is for the 2 matrices. This is for W matrix in the forward, 200 cross 300. This is the U matrix in forward, and this is U matrix in backward, and W matrix in backward, right? So these will be the parameters. You add these and you will get the final parameters, ignoring the bias terms, okay? So this is easy computation. You can do that and see, okay? Now let's continue this problem with another twist. Now suppose you also want to train the word embeddings for a vocabulary of 40,000. So that means you are using NER data to also train your word embeddings. So this gives you another concept that while you are doing RNN, it's up to you if you want to even train the word embeddings. That is possible. Why? You think about the input. So input, you are giving the 300 dimension embedding. We were assuming till now that they are already pre-trained. I mean, they are already available to you, and you would not fine tune them further. But you can also fine tune them. How exactly you will do that? So what you will do, you will feed a word as one hot vector. So whatever word is the input, you will feed as a one hot vector. So it will be 1 here and 0 everywhere else. And you will have a matrix that goes from vocabulary dimension to the embedding dimension, right? So from vocabulary to embedding. So this is the dimension. So V times E, right, or you call it D dimension, whatever. So V cross D dimensions of this matrix. What does this matrix denote? it denotes the word embedding per word in the vocabulary. So, for each word in the vocabulary, you have a d-dimension word embedding, and you can make this matrix trainable. So, if you make this matrix trainable, what will happen? The loss will propagate up to this matrix, and you will also be able to fine tune your embeddings with the task. And many times people do that when they have sufficient data, because there are a lot of parameters, you need sufficient data to be able to fine tune your word embedding. So, it may happen you start already with word2vec and further fine tune those, or you can even start from scratch, and just from scratch you can train the word embeddings with this model, right. So, how many additional parameters you will have to train them? So, you have vocabulary of size 40,000 times the word embedding dimension that was given as 300. So, these are additional parameters that you will have to train. Okay. Hope this concept is clear to you from these two questions. Now, let us come to the sequence to sequence problem, and we start with the task of machine translation, and that has been the one of the major story, like success story of neural machine the encoder decoder architecture, deep learning models, that they could be used for machine translation, right. So, what is the task? The task is very simply defined, that is, you have a sentence X in one language, and you want to target it into another sentence Y in a target language, right. So, here you have a sentence in French, and that you want to translate into English. So, you can vary the source and target language, and you should be able to do the translation, right. You all use Google Translate and others, Microsoft Translators, and various other services for this, right. So, in general, when we say sequence to sequence, you can think about any input sequence that has to be converted to another output sequence, right. That will become a sequence to sequence task, like summarization. So, you are taking a document as input, maybe a research article, you want to say, okay, I want to find a summary of that. So, from a long text, you want to get a short text. So, it can be solved using a sequence to sequence paradigm. Similarly, dialogue. You have the previous utterances, and you want to tell what should be the next utterance, right. That will also be a sequence to sequence task, and there are many more. So, how do we typically solve these sequence to sequence tasks? So, let us focus on the encoder decoder architecture that we will be using. So, you have an input sentence, say it has nx words, and you want to get an output that has ny words, right. So, you have a sequence at input, and you want to generate a sequence at output. So, how do we solve this? We take the RNN both for encode the input and also to decode the output. So, encoding means you are taking the input sentence and creating a representation for that. That is called encoding. So, create a representation for this, and that is encoding. And decoding means using this representation, now you start generating the output, right. So, again you use a decoder RNN for this. So, it is conditioned on the representation, and it will generate the output sequence, okay. And the length of the input and output can vary from one another. Nx and ny can be totally different. Ny can be larger than nx, can be smaller than nx, depending on the language and the actual sentence that you have taken. So, what is the architecture? Architecture wise, you would see it's not too much of innovation. You can see it as a combination of, say, text classification and language modeling. Like what we did in text classification, we took a sentence and created a representation, right. So, this is what we are calling it as the context. So, you take the input sentence, feed into RNN encoder, and you create a context that is nothing but a representation of the input. In classification, we took this context and classified into some classes, but here what we will do differently, we will take this context now and start generating, like we did generation in the language modeling generation, language model generation, right. So, you can think of it as a combination of a classification and LM generation, language model generation paradigms. So, you combine them. So, you create a context out of that. So, encoder will take a sequence x1 to xn and generates a corresponding sequence of contextualized representation. So, we will get h1 to hn. right? You will get n different representations, right? Now you can use, actually in general you can use any architecture. So LSTMs we'll talk about, they are just more fancy RNNs. So you can use CNNs, we will also see in transformers, they all can be employed as encoders. So this idea is very, very generic. So you can take a sentence and create an encoding of that. Now, so this encoding, from this encoding you get a context, which is a function of all the hidden states, right? Like we did in the classification, we can use a function of these hidden states to represent my sentence. So it can be a function of these, right? And it should convey the essence of the input to the decoder, because this is the only signal typically that goes to decoder, right? So decoder will accept this context vector as input and generates a sequence of hidden states again, and from which it will generate the outputs. Okay. Okay. And you can use any architecture for this. So this was very similar to how you did LM generation. Okay. So then let's look at the objective again for machine translation. What do we have? So you have is English source sentence, the green which arrived, and you want to translate it to Spanish. And this actually is crossed as just a permutation of this, arrived the green bridge. Okay. And let us say X is my source sentence and Y is the target text. What will my encoder go to architecture will do? See, X is given to you, you want to generate Y from scratch, like you have not been given any word of Y. Okay. So you have to compute the probability of Y given X as probability of the first word you generate, Y1 given X, then condition on Y1 you generate Y2. So Y2 given Y1 and X, then condition on Y1 and Y2 generate Y3, and X is always there in the condition. Okay. So you see, it looks very similar to language modeling, right? Except that you have this X as a condition everywhere, right? So this is why it is also known as conditional language model, because you have this condition appended in the every probability. Now we have anyway seen how to realize these probabilities through RNNs, right? Language model. Now you just have to give this conditioning separately. So how is it done, right? So this is what we are showing as the inference time. What will happen at the inference time? So you have the source sentence, the green which arrived. What will happen? So this is the RNN encoder. It will take the words through the embeddings, and inference time means all the parameters are already trained. So you have this matrix W, and you get the hidden state H1, and you have this matrix U. So this will keep on, you will keep on getting the hidden states up to you go to Hn for the last word, right? And by default, what you would do, the last hidden state is itself is called the context, because it captures all the information up to that point. So now you use this Hn to start generating, right? So remember in LN generation what we did, we started from maybe a 0 vector, right? We had a 0 hidden state, 0 vector. But now this may not be a 0 vector, you can think of this as your H0, the initial hidden state from which you are starting. Okay? And you have a starting of sentence token, like by default you always start with a start of sentence token, and you have its corresponding embedding, and you have this decoder. You can have a different matrix, so you may have U decoder and this W decoder, and you multiply the embedding with this and this with this, apply the nonlinearity, you get your H1 in decoder. First instant the decoder, and from there you will apply this matrix V, you will get a vocabulary dimension vector, apply softmax, get probability, and by default you can take the Rmax, the word that has the highest probability. But we will discuss about this like in one of the future lectures, then what are the ways in which you can generate the next token. But let us say you are having some way in which you can generate one token. So once you generate one token, say LIGO, you will take it as the input for the next sequence. So now again you have its embedding, you have the same matrix WD, you get H2 decoder by multiplying this with the UD, and again you do the same sampling or generation of a word, take it next until you achieve something called an end of sentence, or as we discussed, or you achieve a particular sentence length, you can stop there. Okay. So, the decoder is using only this context information, and actually only the first state of the decoder is using that, and after that it is like exactly like you were doing in the language modeling, generating one token at a time. Right. So, this is how you will do in the inference time once your parameters have been trained. So, the encoder and decoder RNN may not share any parameters, they may have separate parameters. Right. So, this WD, even the dimension of the hidden state may be different. Right. So, what happens at the training time? So, the training architecture remains the same, right. So, in the training you need a sufficiently large corpus of parallel sentences where the input is given in English and the output is in Spanish if you are doing English to Spanish translation. And what you will do? You will have some model weights, right. It may not have been fully trained, but some weights. So, you feed the input through embeddings and you have your encoder matrix. So, this is your W at the encoder side and this is your U at the encoder side. Use that to arrive at the context representation and use this context as the initial hidden state for the decoder RNN. Right. And then you will start from the start of sentence, whatever your parameters are, you get a probability distribution over vocabulary. And now, because you are training, you know what is the ground truth word. So, you know this is the ground truth word. So, you will find out this word in your vocabulary and see what is the probability you are giving, and you say minus log probability of the word as the minus log probability of the ground truth as the training signal, as the error signal, right, the loss function. Use that to back propagate. But what would you feed at the next input? Would you feed the word that you actually got the highest probability, or you will feed the word Lego, right? So, what is done in training? Typically, you feed the ground truth word. Otherwise, what would happen if you will feed the largest probability word? In the beginning, it may be any absurd random word, and whatever comes next will not make much sense. So, you actually feed the ground truth word even if this was not the word with the highest probability. So, that is one change that happens from training to inference, right. In inference, you have to actually feed the word that you have selected, but in training you may not, right. You can give the teacher forcing. This particular concept is called teacher forcing. So, you force it to use the ground truth token, and now from there you start generating the word, and you keep on doing that until you have achieved the final end of sentence, right, because you are anyway comparing with the ground truth. You stop wherever is the end of sentence, right. So, stopping criteria is very easy in training time. So, whenever the ground truth is end of sentence, you stop. Okay. Now, you can do certain variations of this architecture. For example, I may want to say that I want to make this context available at each decoder steps. Till now, this from the encoder, the last hidden state HEN was only available to the first step of the decoder, right, as the initial hidden state. But later on, only this was getting fed to this. So, everything that it has to know about the input comes from H1D, right, and it also has information about what is the first word that you are generating and so on, right. So, it's too much information packed there. So, what you can do differently, you can also feed this hidden state, the last hidden state, the context vector at each point in the decoder, right. So, that is another variation in the architecture. So, there is another architectural variation that we can do to make sure that this context that we have is available to all the decoder hidden states. So, what we can do right now, this context is only going to the first hidden state of the decoder, but we can have another matrix by which we can pass it through all the hidden states of the decoder, right. So, this would typically be helpful, because otherwise what was happening, if you go to any hidden state like this, the only information it is getting about the input is from the previous hidden state. It has no direct connection. So, we can make this connection to ensure that this hidden state is actually the context vector is actually passed to each step of the decoder. Okay. So, that is another variation. Now, this RNN has been a huge success, the models inspired from RNN in translation. So, typically in the production setup, what was done, you can use multi-layer RNN. So, where you may have, say, in encoder you may have say 3 layers of RNN, decoder also you may have 3 layers of RNN. Now, we have not talked formally about multi-layer RNN, but the idea is very simple. What will happen? So, if you have say the second layer, the input will not be embedding, but the output from the hidden states from the previous RNN, right. So, the hidden state that you have at the first layer will become the input to the second layer, and similarly the hidden state that you have at the second layer will become input to the third layer RNN, right. Everything else remains same, right. For an RNN you only need where is the input coming from, and otherwise you can just keep on getting the hidden states. So, here the input comes from the previous hidden state in the previous hidden layer. Okay. Same way it happens in the decoder. So, decoder also you may have multiple RNNs, and the hidden state here gives you the input and so on, and only at the top layer, the final layer, you make the prediction of the word, and that goes as the input for the next RNN, very similarly. And these were the kind of models that were used for translation in production. So, I mean, it started as a research attempt in 2014, it became a success in 2016, right, and the first paper came in 2014, and 16 Google Translate has switched from the normal machine translation models to neural machine translation, and by 2018 nearly everyone had, right. So, you have all these companies that have started using neural machine translation as the default engine for machine translation, and that was like one of the main success stories of deep learning. So, now so we talked about feeding this information at every point, but still there is a bottleneck that we can see. What is that? That is the context vector of the last time step of the source text. It has to represent everything about the input, right. Even if you make a direct connection, it has to represent everything about the input, even if it is very long. You may think about summarization, you have a long document and you are summarizing into a short text. So, this has to represent everything about the input. Now, that is a bottleneck. I mean, this is a fixed dimension vector. How will it actually represent everything about the input? So, what is done to avoid this bottleneck? So, the interesting idea that came in was that you can use some sort of attention where the decoder states can attend to all the encoder states. So, they will have a direct connection to all the encoder states, and whenever you are generating, you are not saying I have a fixed context vector. You may have a dynamic context vector. Every time you can see how do I go back and make use of the input and call it my new context vector. So, this context vector will become dynamic. So, I can have a different context at each step of my decoder. Okay. So, each step of my decoder, so what will happen? I have a hidden state. I will try to see some sort of similarity of this hidden state of the decoder with the encoder hidden state, and use some weighted average of the encoder hidden state. Okay. And you may recognize this term as some sort of softmax and doing some weighted attention, weighted average, and you get a new context vector. And this will be different at different time step. So, for example, what actually happens? So, let us say, so each hidden state of the decoder will be able to see a different and dynamic context, which is a function of all the encoder states. So, what will happen? So, the context vector Ci is generated new at each decoding step. How? So, at each decoding step, now it becomes a function of the previous output that you generated, because that is fed as the input, the previous hidden state and the context vector, right. And how do you get the context vector? So, this was like what we saw in the architecture, where you can feed the context vector at every time point, right. So, this context vector, but now we will make a dynamic context vector. It is not the fixed context vector at every step. So, how will we make this context vector? So, we will focus on, so we will see how to focus on each encoder state by seeing how relevant it is to the last decoder step, right. So, suppose you are at the ith step in the decoder, you want to compute HDI, and for that you need the context, right. So, how will you get the context? You want to see, okay, I will see hi minus 1d, how similar it was to each step of my encoder. So, I will compute similarity of hi minus 1d with all the states of my encoder. It can be a dot product. There are other variations of also, but this is a simplistic formulation. You just take a dot product. If the dimensions are not same, you cannot do dot product, right. So, now once you have the scores, so you have as many scores as the size of your input, right, because for each hidden state you have a score in the input. Now, you take a weighted average of each. So, how will you do? So, first these scores you convert into probabilities using softmax. So, this become the weights, and now you take a weighted average of all the hidden states. So, you do alpha ij times HJE summation over all j. This becomes your new dynamic context, and that you use to feed to get your new hidden state HID. Okay. So, that is what is done in attention. Now, you can try this problem. So, suppose you have an RNN sequence to sequence RNN model with attention, and it has 4 hidden states, right. So, these are the at the encoder. So, you have 1 minus 1, minus 1 1, 0 minus 1, minus 1 0. In the decoder, you are doing at some time step I. Now, suppose this is minus 1 minus 1, the hidden state. So, when you go to I plus 1, what will be the context vector for this, right? How will you find that out? It is very easy. You will say, okay, I will use the previous, this is the previous step of the decoder, state of the decoder. I will take its similarity with all of these. So, what will be the similarity? Minus 1 times this will become 0, same will become 0, become 1 and 1. This is the similarity. Now, I will put in attention. So, I will put a softmax over that, and softmax will be nothing but e to the power 0, e to the power 0, E1, E1 divided by 2 times E naught plus E1, right, is equal to G. You compute these weights, right, suppose alpha 1, alpha 2, alpha 3, alpha 4, and you will take a weighted average of these hidden state times alpha 1 times alpha 2 times alpha 3 times alpha 4, and this becomes your context vector to the next hidden state, right. You can try this out and see what is the output that you get. Okay. And attention has been very, very helpful. So, for example, people have seen this attention actually improved, like that is the why it became popular, the performance of neural machine translation, because it allowed decoder to focus on certain parts of the input sentence, right. That was not previously possible. And it also gave you some interpretability, because when you focus on certain parts of the input, you can find out while generating this word, what word in the input I focused on. So, this gives you some sort of interpretability also, and you also can get an alignment for free, like what is the word that where you had put the maximum attention. Okay. So, like this is some example like that people have seen in this paper, neural machine translation by jointly learning to align and translate. So, they tried multiple sentences, right. Let us look at this sentence, and what you are seeing at the bright spots are the places where while generating this word it had put the maximum attention on, right. So, because attention has weights, you can see which word had the maximum attention. So, agreement had the maximum attention to accord, which makes sense. Similarly, European has on European, economic had on this. Even if the word order was different, it was able to focus on the particular word, right. Similarly, August, if you see, will focus on out, right, 1992 on itself, and so on. So, this gives you some interpretability that while generating this word, what word in the input you actually focused on. That same thing you can see on the other sentence also, environment on this and so on. Also in summarization, so this is your input and this is the output, and you can see while generating the output, the shorter text, the terrorism focused on this, but against focused on combating. You see there are different words, but against, for generating against, you focused on combating. Similarly, you have calls focused on called and so on. So, you can find nice interpretability with the attention mechanism, and we will actually go a lot many details when we talk about transformers, right, but this became popular even with the LSTMs and RNN sort of architecture. And so chapter 8 of the book actually will give you more idea about this concept. So, okay, so thank you all.